So in the first part, we will introduce a new simulation algorithm based on something called the interaction picture, and then apply this to improving the quantum simulation of chemistry in second quantization. In the second part, Dominic will talk about applying this method to getting really nice results in first quantization for chemistry. So why should we care about quantum simulation? There are a few reasons. So one reason is that it is universal. You can simulate the gate model of computation using it. So it's as good a starting point as any for understanding quantum computation and what we can do for it. Simulation is also a primitive used in many other interesting algorithms, such as solving systems of linear equations and for Gibbs sampling. So improvements to simulation also directly leads to improvements in these other results. And perhaps last but not least is that simulation gives us a really good answer to this question of what can you do with 100 qubits that investors really like to hear about. For instance, we can, in principle, accelerate the discovery of drugs, use it to, say, design better catalysts for fertilizer or perhaps for fuel production or maybe even batteries. In other words, quantum simulation is one of those applications where we can realistically hope for an exponential speed up for problems that are of great technological interest. And this is especially important because classical methods for simulating quantum systems scale exponentially, whereas we really believe that quantum simulation on a quantum computer would scale polynomially. So what exactly is quantum simulation? In this case, I look at the case of Hamiltonian simulation, where our quantum system is represented as a Hermitian matrix, the Hamiltonian. In the simplest possible instance, this Hamiltonian is a sum of just two parts, A and B. And our goal is to come up with some quantum circuit that well approximates the real-time evolution operator by h for time t. This solves Schrodinger's equation, and that's basically it. So the first main approaches for creating this quantum circuit for simulation was based on product formulas introduced by Seth Lloyd and with many, many other improvements over the years, but unfortunately I can't talk about them. These product formulas are really simple. If your Hamiltonian is a sum of two parts, and we can simulate each part easily, let's just alternate between the two. And if we have small time sets for each of the two and just apply them many, many times, we can well approximate time evolution by the whole. Then more recently, we have had further developments in quantum simulation, which is everything but product formulas. So we call these a post-product formula approach. And there are quite a few ways to do this, but most of them generally fall into this process flow that you can kind of see here. If we start with time evolution by a part, we can use, say, various techniques to take a matrix logarithm of that and block encode the Hamiltonian you want in some bigger matrix. So in Andres' talk yesterday, he mentioned block encoding, and just to reiterate what that means, this matrix here is a quantum circuit. It's a unitary where we've designed it so that the Hamiltonian we care about is in the top left block. So if you were to project onto some basis, you'd be applying that Hamiltonian. This is a block encoding. Now, given a block encoding for the parts, we can use very standard techniques, such as those made by Andrew Childs and Dominic, linear combinations of unitaries. To combine the block encodings, we can combine them to now have a block encoding of the full Hamiltonian. Then we can use techniques just to throw some words around like qubitization, which converts a block encoding into a quantum walk. The quantum walk has the nice property where a spectrum depends on the Hamiltonian you've block encoded. The block encoding itself has no spectral information that depends on the Hamiltonian. So, now that it is a quantum walk, we can use various techniques like quantum phase estimation or quantum signal processing to linearize this phase factor and get real-time evolution. So regardless of what approach you use, in the case where we have no more information about the structure of our Hamiltonian, just know that there's a term A and a term B. These approaches are basically optimal up to, say, logarithmic factors. The cost will be basically linear in time, linear in the sum of the norm of your terms, and linear in the sum of the costs of implementing each term individually. Like, this is the best you can do. And if you want to go further, we need to start making assumptions on some special structure of our Hamiltonian. And now the challenge is that we want to identify structure that is specialized enough that you can actually exploit it to speed up simulation, but not so specialized that it doesn't exclude problems that we might care about. So the interaction picture algorithm that I will talk about is one of those pretty general structures that still happen to be very useful. particularly for quantum chemistry. So the general way to understand this structure is that of diagonally dominant Hamiltonians. So diagonally dominant matrices are pretty common in classical computation. Basically, it means that in some known basis, your Hamiltonian has a diagonal that's pretty huge. So to draw some intuition from physics, imagine kinetic energy. Kinetic energy is diagonal in the momentum basis, and it could have a really, really large spectral norm because you could just have really, really high energy plane waves. But in the position basis, we might have, say, a potential term that perhaps represents low energy excitations. So if A is kinetic energy and B is potential energy, the strength of A could be much bigger than the strength of B. And if we were to use the unstructured generic simulation algorithms for this problem, we are basically combining the worst of all worlds. Our cost is dominated by the strength of the biggest term multiplied by the largest cost of implementing any of these terms. So we want to avoid this worst case. We want to realize something that's more like an average case. And in our interaction picture simulation algorithm, we can move this huge term that's just really expensive to simulate in terms of the norm into the logarithmic factor. And how it works, I'll talk about later. And what's really nice about this algorithm is that you can recurse it to kind of realize an average case for multiple terms, where instead of looking at the sum of the product or sum of many things, you kind of look at just a pairwise sum of the cost and the products. There's a catcher in that the more terms you have, the larger your prefactor is. But this still happens to be optimal in a certain query setting. So what do I mean by optimal in this query setting? This is a pretty standard picture for how you represent Hamiltonians in a computational framework. You assume that your Hamiltonian is d-sparse. This means that in every row and column, you only have d non-zero elements, even though the whole Hamiltonian itself might be exponentially large. And to produce these elements, you assume access to two oracles, one oracle that tells you the values of these elements in, say, the ith row and jth column, and one that tells you where these non-zero entries are. This is a pretty standard assumption for evaluating the query complexity of Hamiltonians. And in this framework, there have been many results over the years, and also, unfortunately, I can just only show a few of them. The main takeaway messages here is that people usually express cost in terms of a few factors that you kind of know beforehand. For instance, you might know what is the maximum value of any term in your Hamiltonian, that's Hmax. You might know what is the number of non-zero elements, that's the sparsity D, and you might pick a target error and a target simulation time. So the first result that achieved optimality in more than one of these parameters was by Dominic Berry and Andrew Childs. So essentially, you have your linear scaling in time, linear scaling in sparsity, and linear scaling in max norm. Then in more recent work, the scaling in respect to error was improved to a logarithmic factor, then finally to an additive factor, which is optimal. But the max norm is not the only way we know how to characterize Hamiltonians. Quite often, we have additional information on the structure of a Hamiltonian. For instance, we might know the spectral norm. And if we know the spectral norm, perhaps this is something we can use to speed up simulation. And so in the work by Berry and Childs, they also figured out how to make the scaling of sparsity better, so now it's d to the 2/3, but you pay a cost. The time scaling and is now worse than linear. And maybe the spectral norm is too much. How about the one norm? The one norm is the sum of the absolute values of all entries in the column. You can kind of intuit it as how strong does any state interact with all other states. And if you know that, you can also improve the scaling with respect to sparsity. And this interaction picture simulation algorithm, which you recurse, allows us to get a general result that actually encompasses all of this up to sub-polynomial factors. What I mean by that is that we can express the cost of simulation as linear in time, square root and sparsity, and this weird norm here, this is a subordinate norm, it's a sum of squares of every column. And what is cool about this is that you can plug in any upper bound of this norm into this algorithm, and you can basically, from these sequence of inequalities, recover the scaling of all of these earlier algorithms. And why this is interesting is because it allows you to now get speed-ups for other quantum algorithms that use simulation as a subroutine, such as, say, linear systems. Previously, you had linear scaling and sparsity. Now you just plug in this algorithm, and you get square root scaling and sparsity. It also resolves an abstract problem where instead of specifying a Hamiltonian with these oracles, you instead specify a unitary, and you're going to implement these unitaries. A lower bound for that is square root d because of Grover search, and now we can achieve that. So how does this interaction picture simulation algorithm work? Before we get there, one important primitive that I think is good to talk about is linear combination of unitaries. Suppose you have a unitary that is a sum of more unitaries, and they each have some coefficients. We want to create a quantum circuit that block encodes this unitary. So the circuit that does it is pretty straightforward. We create a quantum state where we have our coefficients as square roots of some index state. And if we sandwich an operator that applies the Elf unitary conditional on state L, we basically get on our system psi, our target unitary divided by some normalization factor. Our interaction picture simulation algorithm is built up by combining this LCU approach with time-dependent simulation. So when I introduced simulation earlier, I was looking at the time-independent case, but we all know that in the general case, Hamiltonians can be time-dependent, and we want to find out what is the time evolution operator that solves the time-dependent Schrödinger equation. So this is no longer a simple exponential of just two terms. It's not really complicated, but you can still express it formally as something that's called the Dyson series. This is analogous to the Taylor series, and it's represented as nested integrals of your time-dependent Hamiltonian evaluated at different times. If you just kind of stare at the order of integration, this is integrating under a simplex of some hypercube. The dimension of this hypercube, this is k. This is the order at which we truncate our Dyson series, and we choose this to achieve whatever target error we want. So now, this is in terms of integrals, but we can't do integrals on a quantum computer. We can only do sums. So this means we need to discretize the integrals. And if you just do some analysis, you'll find out that the number of points you need to discretize the integrals at scales linearly with the error, 1 over the error, and linearly with the time dependence of your Hamiltonian. So that is a maximum spectral norm of the time derivative of your Hamiltonian. It's a bit of a mouthful. And now that we have expressed our integral as a sum, one can note that this is a sum over a uniform distribution over a k-dimensional simplex. It's actually not too hard to prepare this state. And if you were to create this state as a thing that you use to select the terms in a Hamiltonian, you can actually just directly approximate this time-ordered evolution operator. The cost of doing so is expressed in terms of queries to the block encoding, except that instead of a block encoding to your Hamiltonian at a single time, it's now kind of like a block encoding to Hamiltonians evaluated at many different times. Your diagonal is now the Hamiltonian at time 0, time 1, 2, 3, and so on. And let's call the cost of this block encoding C sub ht. I'll talk more about what exactly this value is here. But if you mash these factors together, you'll find out that the cost of simulation is going to be linear in time. It's going to be linear in the spectral norm of your Hamiltonian. That's the maximum spectral norm. It's going to be linear in your cost of this block encoding. It's going to be linear in k. And now we have the cost of this uniform superposition over simplex. That's the log of n points because it's a uniform superposition. So this time-dependent simulation algorithm is what we use for the interaction picture. Instead of the Schrödinger picture, where we have a time-independent Hamiltonian, let us use some kind of prior knowledge about the structure of Hamiltonian. We know that one of these terms is enormous. That's the A term. So let's factor that out. That seems like a good idea. And that's basically the interaction picture. So we go to the rotating frame where we look at the time evolution of this state that is where we factored out time evolution by A. And now if we just plug this into Schrödinger's equation, we find out that the A term in our Hamiltonian cancels out, and we are left with a time dependence term. It is the B term of a Hamiltonian now rotating in the frame of A. So at first glance, this seems like a crazy idea. Time independence is simple. Why would we make our lives difficult? That algorithm for time-dependent simulation seemed a lot more complicated than just the product formula. So the reason why turns out to be in how the time dependence of simulation shows up in the logarithmic factor for the time-dependent simulation algorithm. This means that you can have things spinning really, really fast. If you were to look at the spectrum of this time dependence, that could be enormous, but since it's in a log factor, we don't really pay that price. So now if we use our time-dependent simulation algorithm to simulate the time-dependent Hamiltonian in the interaction picture, we can now kind of get something that looks like a bastardized version of the product formula. Rather than alternating between time evolution of A and B, we now alternate between time evolution of A followed by a residual thing that captures everything else. So you can kind of think about it as combining product formulas with LCU approaches, and that could be something interesting to consider in the future. So now, because of block encoding, this time-dependent Hamiltonian, you can see that there's a B term, and we sandwich it between these two time evolution terms. So essentially, the cost is going to be the sum of these two, with some log factors due to say discretizing a time register into multiple parts. And if you were to just throw all of these parameters into the time-dependent simulation algorithm, you get our result for the cost of simulation interaction picture. You get your linear scaling with the smaller term, B, and time. And the norm of A is now represented in the norm of the time-dependent Hamiltonian, which is just the commutator of A and B. And so, that log factor is something we can just ignore. And how can we apply this to simulation of chemistry? So typically, when we think about chemistry, we usually choose a basis set of orbitals. So for hydrogen, this would be your hydrogen basis sets. But you could also choose linear combinations of these atomic orbitals that kind of captures where your electrons live. And in this basis set, we can express our Hamiltonian as a linear combination of fermionic operators. And there will be at most these two body interaction terms where you have a sum over PQRS. PQRS index the orbitals. And in the worst case, there are going to be n to the 4 of these terms if you have n orbitals. So now if you think about just the worst case, the cost of simulation and second quantization in this basis is n to the 8. And that's pretty bad. But it turns out that instead of choosing an unstructured basis such as Gaussian basis, you can use the plane wave basis. Plane waves are pretty natural for periodic systems. And in the plane wave basis, it turns out that if you're to take a discrete Fourier transform of this basis, you get something that's called the dual plane wave basis that kind of approximates the position basis. In this basis, your chemistry Hamiltonian greatly simplifies. There are only going to be n squared terms. And now we want to simulate chemistry using this basis, using the fact that it's highly structured. So using a standard Jordan-Wigner encoder, you can convert this from a fermionic basis to qubit operators. And the main takeaway message is that the potential terms, they are diagonal in, say, one basis, and the kinetic terms will be diagonal in a different basis that is obtained by something called the fast fermionic Fourier transform.
I think we need to let the next speaker go on.
Right. So now, if you want to apply this to second quantization, it turns out that if you just look at the cost of implementing these terms and you plug them into the interaction picture algorithm, you get our results, which is quadratic scaling in the number of orbitals compared to the very worst case of Gaussian orbitals of n to the 8. So now Dominic will take over, and thank you.
Okay, I'll see if I can get this working. Hello? Hello? Not working? Okay, I think I'll just use this one since the, sorry? Yeah, I'll just use this one. Okay, so now I'll talk about how to achieve better scaling for some situations. So for what Guanghao's just been showing you, the idea is that you have the B, which is the thing which you're paying the cost of the norm of, and you have an A, which is a thing you're going to have to rotate under. So we have the Hamiltonian for these chemistry systems where you have a kinetic term and a potential term. So when you're doing things in the second quantization, the potential energy term is going to have a larger norm, and the kinetic energy term has a smaller norm. And for that reason, you want to take the kinetic term and call that the B and rotate under the potential energy. So the reason why you have a large norm for the potential energy is that the representation you're using is allowing up to n electrons, where n is the number of orbitals. So your potential energy can have up to n electrons, and those electron-electron interactions can have energy that each goes roughly like n over the volume to the power of 1/3. So that gives you an overall norm that's going like n squared times n over omega to the 1/3. So that gives you a norm for your potential term that's roughly going like n to the 7/3 there. So it seems a bit pointless to pay a cost for electrons that aren't really there. So what we'd like to do to get a better complexity is to use a representation where we only allow as many electrons as we actually have. So if you're only allowing eta electrons, so the symbol I'll be using here for the number of electrons is eta, then the norm of the potential is just going to go like eta squared, the actual number of electrons, times n over eta to the power of 1/3. So if you're looking in terms of the scaling with n, this is much better because your n to the 7/3 is turned into an n to the 1/3. And the idea here is that we're actually wanting to look at scenarios where we have a very large n, many orbitals, but a smaller number of electrons. And when you use this representation, the kinetic term is then going like n to the 2/3. So this is basically swapped around which one has the larger norm. So when you go to the first quantization, the kinetic term has this n to the 2/3 and it's larger, whereas with the second quantization, the t was actually smaller. So I'll quickly explain how the first quantization works. So the idea with the first quantization is that instead of using a whole string of qubits where each qubit is just 1 or 0 to indicate whether an orbital is occupied or not, what you have is a string of eta registers, and each of those registers is giving you a number for an orbital that's occupied by an electron. And there's a subtlety here that you have to take account of anti-commutation relations for fermions, and that's done by taking anti-symmetric combinations of these basis states. Now, then when you're using that representation, we're having this B, which is the thing that we're implementing using a linear combination of unitaries, now being the potential term, and then that has this n to the 1/3 scaling. And that will turn out to be the dominant contributor to the complexity. But to look at how the overall algorithm works, you have to take into account how you do these evolutions under A, which is now the kinetic energy, and how you do these linear combination of unitaries applications of the B. So the kinetic energy is relatively easy to evolve under here. So the representation that we're using is now plane waves, and so each orbital is corresponding to a plane wave of a particular momentum. And your representation is just a whole lot of registers which are giving you momenta for particular electrons. So you just have to take the norm squared of each of these and sum them up, and that's giving you a kinetic energy, and you can just apply a phase factor according to that, and it's giving you evolution under the kinetic energy. And the overall complexity of this is going like the number of electrons that you have times logarithmic factors. So when I'm writing the complexity, I'll write these in terms of O tildes, which is indicating that we're ignoring log factors, and we have an O tilde of eta here. And that was the wrong way. Here we go. So next we need to look at linear combination of unitaries applications of the B, which is now our potential energy. And the potential energy, I'll just quickly look at the electron-electron term. So when you're doing linear combinations of unitaries, when you look at your unitary, the things which are appearing as indices in these sums are typically the things which are going to have to go as control registers, and you're going to want to do the operations in the sum in a controlled way, and you're going to want to prepare a state that's proportional to the square root of the weights here. So for the controlled operations, it's essentially this here, and what that means is that you're subtracting a momentum nu from register J and adding it to register I. And you can essentially do this just by running through the registers and doing arithmetic, and that gives you another factor in the complexity of O tilde of eta. The tricky thing is to do the state preparation. So the state preparation we use is essentially based on a the type of state preparation proposed by Grover back around 2000, which is very similar to the Grover search. And it basically involves a rotation to get you amplitudes that you're looking for, followed by a whole sequence of amplitude amplifications. And if you were to do it directly, you would just end up having a complexity which is scaling like n. But we have some clever tricks to make the complexity logarithmic. And I'll skip over that since we're running out of time. So the overall complexity is now these O tilde of eta factors from controlled operations and applications of evolution under the kinetic energy multiplied by that norm of B. So we get overall complexity that's going like n to the 1/3 times polynomial factors in the number of electrons. And that's quite amazing when you consider that initial algorithms for these types of problems had scalings going like n to the 10 or n to the 11. And we also have a number of qubits, which is logarithmic in the number of orbitals. So if you're looking in different scenarios, you would either want to use the approach that Guang Hao proposed or the one that I've just explained here. So the case where you'd want to use Guang Hao's approach is where you have high occupation numbers, because there you're paying a cost of n there as well. And if that number of electrons is going like n, that thing is actually going like n cubed instead of n to the 1/3. And then Guang Hao's scheme actually goes like n squared. So if you look at realistic scenarios, you would be getting orders of magnitude improvement using Guang Hao's approach. And I should mention as well that this is omitting some constant and logarithmic factors, but they should be the same for the two algorithms. But if you have something like, say, plane wave representations of molecules, you're going to want to use many, many more orbitals than you have electrons. So in this example, we have only 40 electrons, but 1 million plane waves. And in that case, Guang Hao's approach goes like 10 to the 15 there, whereas ours goes like 10 to the 6. So you're getting about a factor of 1 billion improvement. So I am almost out of time here, so I'll just go to the conclusions, which is just explaining again that we have used the essential things we've used here are the plane wave representation in quantum chemistry and the interaction picture, and we have looked at second quantization first and first quantization second, and this one you want to use if you have systems with high occupations, and this one you want to use if you have very large numbers of plane waves. Thank you.
So
All right.
just a brief message. We have a lot of socks, so visit our booth to get some.
All right, so we have time for questions. Any questions? We still got time.
Here's a hint for a question. You might want to ask why we can do these integrals efficiently if we have a vast number of points that we have to integrate over.
Any takers for that question?
Okay. So the neat thing with these...
You've got to repeat the question in your own words. Otherwise, it's not a legit question.
The neat thing with these linear combination of unitaries approaches is that you can do sums over things and only pay a logarithmic cost in the number of terms in the sum. So if you're looking at the sum, the actual complexity that you're really paying there is essentially the integral of the weights there. And you're not actually paying a cost of the number of terms in the sum except as a logarithmic factor. So that expression that Guang Hao showed you with that 1 over epsilon, it only turns it into a log 1 over epsilon in the complexity.
Any other questions? A question here?
So in your interaction picture approach, do you have to assume that the Hamiltonian is varying slowly with respect to some energy gap?
There is no such assumption. However, one question which I've heard earlier in this conference is if we know that our states live in a low energy space, can we kind of use this? The interaction picture approach kind of offers a partial answer to this. Let's say you have very high energy kinetic terms, and the really interesting stuff happens in the low energy potential sector. So, this is maybe one way to make it better, but it's very case dependent.
We still have time for another question.
Over there.
So you said that one of the dominant costs was multiplication. So if you use like one of the fancy multipliers with n log n something complexity instead of n squared, they have like worse constant factors, but does it make the asymptotics better?
In principle, it makes the asymptotics better, but the clever multiplying algorithms tend to be for thousands of digits, so you don't want to actually use it in any realistic scenario.
Thank you.
All right, let's thank both our speakers again.